The next presenter is the project coordinator of ShaleX. So essentially, the reason that we're all here is because of Alberto Striolo, who coordinates this activity on shale gas. Professor Striolo, he's a professor of molecular thermodynamics at University College London, and before that he was a professor of chemical engineering at University of Oklahoma. He has done research on Lawrence Berkeley Laboratory and Princeton University and got his PhD from University of California, Berkeley. He's one of the leaders worldwide in the field of molecular thermodynamics with emphasis to confined fluids. And as I mentioned, he's leading the effort on shale gas for the last almost 3 years now, and we'll be happy to have him here today to give us an overview of the project. Alberto. You need the pointer?
That should be all right. And he can never tie. Thanks for the kind introduction, Yannis. I would like to start by thanking you for organizing the whole event. It looks fantastic, and I'm sure it will be a very productive day. I would like to thank Qatar Foundation for funding this event. Without money, we cannot do these things, so thanks a lot. And I would like to thank Texas A&M for hosting us. So maybe I should say Audi. And I would also like to thank all of you for finding the time to be here. It is an honor for me to present what the consortium has been able to do over the past couple of years. My role is just to give you an overview of what the whole consortium is trying to do, and then during the day we will learn more about the details about what each of the groups is doing. The consortium is ShaleXenvironmenT. We are well into the second year of the project, and the project will end in August. And last September, we were lucky enough to start a new European project. It's called Science for Clean Energy. I will give you a few hints about what that project is all about, and perhaps we see how we can start collaborating together. So overall, we are doing fundamental research. We are doing everything we can to move forward the technology and to quantify the environmental impacts so that we can minimize them. And the scope of today is really to try to identify possible new collaborations to move this project forward. So perhaps I should start by reminding to this audience why we are interested in natural gas. So for example, in this cartoon on the upright, what we have is this one over here. These are predictions from the International Energy Agency regarding the energy needs for the next 40 years. And what you see is that there are a couple of spots in red. Those are diminished requests in energy, mostly in Europe. But for the rest of the world, what you see is that you have a lot of yellow bubbles. So what that indicates is that the demand of energy for the next 40 years is going to increase. Natural gas is going to provide at least some of that energy. From the environmental point of view, I want to take your attention to this bottom left graph. These are CO2 emissions in the US over the past 10 years or so. And what we see there is that the CO2 emissions have decreased starting from around 2005. And part of the reason was that some of the energy producing plants were shifted from coal to natural gas. So natural gas offers the opportunity of reducing the environmental impact of energy production sector. On this right corner over here, I report a pamphlet produced by the American Chemistry Council. It's a lobbyist group in the United States. But in this pamphlet, what they advertise is that because of shale gas, there has been an investment on over 250 new chemical projects in the US, which has resulted in the creation of a large number of manufacturing jobs. So shale gas has the potential of creating jobs, manufacturing jobs in various positions. Shale formations are found throughout the world, sometimes in regions where oil and gas is not traditionally found. As a consequence, it is possible that shale gas can open up avenues for energy independence. So there are many reasons why shale gas is attractive throughout the world. However, we should always also remember that there are downsides. Speaking about energy independence, in Europe we have the example of Poland. And over here, I report a graph that shows the number of wells that were drilled to try to produce shale gas in Poland. And what you see is that around 2011, there was a lot of enthusiasm for that technology, but in 2015, only 2 new wells were drilled, and now that experience has, for the most part, stopped. The reason was that it was not possible to produce that gas economically. So we should keep in mind that it is not always easy to produce shale gas. There are technological hurdles that need to be understood. It is possible that producing the shale gas, even though natural gas offers environmental benefits, there can be environmental impacts during the production itself. This is just a list of many possible impacts that can be generated by the shale gas production. They can run from contaminations to the water, they can run to emissions, microseismic events, and so on and so forth. So the operations need to be done properly, otherwise they can lead to undesired effects. When these effects are produced, it is possible that the communities create an opposition to the development of shale gas. And in Europe, we are very familiar with this sort of opposition, and it is becoming clear that the public need to be involved in the decisions, and we need the companies, if they want to operate, they need to obtain the social license to operate. So overall, there are a number of issues that need to be addressed. And what I think is fair to say is that our consortia are trying to develop a lot of fundamental science that is aimed at mitigating the risks. So in preparing this presentation, what I was thinking of was how can I summarize the research that we are doing. And I think that overall, what we are trying to do in our consortia are essentially better understand the asset. We are trying to develop new technology that can be sometimes breakthrough technologies. And overall, we are trying to use this understanding to mitigate the risks and reduce the impacts. So what I will do now in the next few minutes is cherry-pick some of the results that have been produced by the partners in this consortium. And hopefully, at the end of the day, we have this overview discussion. And the idea will be to try to see how we can use this platform that we have developed over the past 2 years to see how we can move forward and perhaps start new collaborations. So let me start by cherry-picking a few of these examples. This is an impressive set of results that has been developed by our colleagues in Manchester. We have Kevin here that is going to give us an overview about those recent results. They have been using the synchrotron in the UK to better characterize the rocks. This is just one of the many things that they have been doing. In this specific example, what they've done is to design, develop, build the instruments that can keep a small piece of rock, a sample, and they can push that piece of rock, and they can start making fractures on that rock. So for example, here you have a metal that is pushed into the rock, and what you see here is that you have the formation of the fracture in there. And these are two analyses of the results, and as you increase the pressure that is applied to this rock, you have the formation of the fracture in there, and that fracture keeps propagating. So they are able to do this in real time and with absolute excellent resolution. I think they are the only one in the world that are able to do this. As another example of what we are able to do, this comes from University College London. My colleagues from the Earth Science Department have been able to use X-ray tomograph to identify the pore network inside of a shale sample. The shale sample in this case was provided to us by Alberto. Thank you very much. It is a commercial sample. It has a lot of clay in it. And what you see here is that those red spots, we understand them as being small little pores that are present in the rock. This is one instrument that we use. It gives us a relatively large resolution in a relatively large piece of the rock. In the other instrument that we have, the resolution increases, and what you can see, perhaps, is that you start seeing the striation inside of the rock. What we think is that those are the pores that are present in the various pieces of the rock. And then when we measure the permeability, what we notice is that the permeability in one direction can be 1 or 2 orders of magnitude larger than the permeability on the opposite direction. And now we have a correlation between the rock pore network and the permeability that we measure. Okay? So these are quite impressive advancements that we have been able to do over the past 2 or 3 years. Importantly, we also need to estimate how much gas can be found in place before we start drilling a large number of wells, for example. This is a contribution that comes from Ronnie Pinney at Imperial College London. These are just the adsorption isotherms. So basically, we are measuring how much gas can be adsorbed in a rock. This happens to be a rock sample from the Boland Formation in the UK. And what you see is that this specific rock absorbs more CO2 than methane. Okay? That has been observed in other rocks by other people throughout the world, and that suggests that perhaps CO2 can be used to enhance the productivity of methane from shale formations. However, the advancement here is in this little number here, 80 degrees. So these measurements can be done at relatively large temperatures. And that advancement is also connected to this other number over here, 250 bar. So Ronnie is able to measure these adsorption isotherms at conditions that are approaching the in situ conditions inside of the formation. So that is a significant step forward compared to what other people have been able to do throughout the world. And this is the instrument that Ronnie has developed at Imperial College. You may not be able to read there, but it says Qatar. So there is funding from Qatar Petroleum that has been able to support this infrastructure at Imperial College. Ronnie will tell us more about this in the next, the remaining of the day. Now, I've discussed a lot of fundamental science that we have been able to do. One of the other pillars that we are trying to advance is the technological innovation. So, for example, here we have an image of a shale rock. If I remember correctly, it's a SEM image. One challenge will be to be able to predict the permeability of gases throughout that little rock. Experiments can be done. I showed you some results earlier, and we will see something more later on in the day. But they are very challenging. They take a lot of time. Is it possible, just by looking at that picture, to be able to predict what the permeability is? To answer that question, we have a large number of teams in the consortium. They are listed there. Well, the symbols are there, the Mokritos, the Yanis, the Czech Academy of Sciences, Armins. We are doing a lot of molecular dynamics simulations to better understand the behavior of the fluids in the various pores. But those simulations, as much as I like them, they can only be done for a single pore at a time. How can we predict what is the permeability throughout a rock? To answer that question, we are using a stochastic approach. Maria, one of the students in my group, is going to tell us how we are trying to do that. And the advantage, we have not really solved the problem yet, but the preliminary results suggest that we are able to pinpoint experimental data using this computational approach that is stochastic in nature. So we will learn more about this when Maria is going to take the stage later on today. In Florence, there is another example where we are using both fundamental science to deliver new technologies. So this is just an example of the type of science that they like to do. We will learn more about this later from Moira. This is the viscosity that is being measured by changing the shear stress of different aqueous solutions. In this case, the aqueous solutions, they contain Wargam. It was one of the first hydraulic fracturing fluids. The important thing that I want to point out here is that all of these curves, they are obtained for systems of the same concentration of Wargam in the same concentration of salt. What changes is the type of the salt. And what you can see there is that the viscosity of those solutions changes by more than 1 order of magnitude, simply by changing the type of the salt that is present in there. Different formations have different salts in there. Perhaps that could explain why some hydraulic fracturing fluids work somewhere, but they don't work somewhere else. The group is now developing anti-scaling agents, and the idea will be to use only products that are green, maybe sugars. And they are comparing the behavior of anti-scaling agents that are used in the industry versus the new ones that they are testing. And perhaps more importantly is that they are putting those scaling agents together with the viscosity modifiers. And they are formulating the green formulations in a way that they are still performing both as anti-scaling agent and as viscosity modifiers. So they will tell us more about this in the next few minutes. This cartoon is a a bit of a plug for the new project, the Science for Clean Energy. There is a lot of input in developing new technologies. And here I want to just briefly mention 3 of these technologies at different stages of development. One, very early stages, is to use tracers that are based on DNA to monitor the transport of fluid in the subsurface. Preliminary experiments have been done together with Ronnie Pini, but it's very, very early stages here. This is another advancement. This is done in collaboration with the University of Eastern Finland. And the idea here is to try to understand how moisture penetrates into cements. We don't want to break the cements, so we want to do experiments that keep the cement intact. And the technique that we are trying to use is electrical capacitance tomography. I need to read that because it's new to me as well. But it seems very promising. So this one is a cement sample, and that blue sphere is the moisture that is penetrating into that cement as a function of time. So laboratory testing are quite impressive at the moment. This is a third example. In this case, we are already at the prototype testing, and this is a collaboration with Mirico. It's a small company in the UK. They are developing spectroscopic-based sensors to detect leaks on the surface. So this is a summary of a field test that they did in collaboration with Shell Global Solution International. So this grid is 120 by 120 meters. And the experiment has been done on the surface. They put the sensor over here. It is an instrument. It is a spectroscopic instrument. It shines lasers. So these lines are the laser trajectories. And in these dots, there are mirrors that shine the laser back to the receiver. They put this on an open path, and they have been able to detect the position of 2 leaks, 1 and 2, of methane on the surface. The expected position was the cross, so they are not exactly where the leaks are, but they are very close enough. They are able to see the leaks, and they are also able to quantify how much methane is being released. So this, we are at the prototype testing, and now we want to develop this a little further, and we are actually quite proud to be able to support this technology, and hopefully it will see commercial development in the near future. We heard earlier that water is important. As chemical engineers, what we do very well is optimization of various technologies. So within SXT, what we've done is a lot of work to optimize the water treatment processes that could be connected to the shale gas operations. This is somewhat a standard chemical engineering problem. The advantage here is that we are connecting it with the specifics of shale gas production. So we are looking into what is the typical composition of a flowback water. We are connecting it with the various fluids that we can use to prevent the scale formations in the subsurface and so on and so forth. At UCL, we are also looking at making sure that accidents do not happen. So this is work done by the group of Magrefet, and we will see something in the afternoon. And essentially, in the worst case scenario, in a case that a well blow up, what can we do? How far should we do from that? How far shall we be from that well to make sure that nothing particularly bad happens to the environment or to humans? And finally, we are trying to bring everything together. We are implementing a life cycle approach to quantify the impacts of the various technologies. And we are, with the help of our colleagues from Australia, we are comparing best practice procedures in the US, Europe, and Australia to find out what is the best way to proceed in a way that ensures that the least possible impact on the environment of the technology. So here is a summary of who we are. Down here are all the partners. Halliburton is one of the partners here, and another company is Geomecon. Geomecon is a small, medium enterprise in Germany. All the rest are academic and government groups throughout Europe. We have a large number of international collaborations. We interact with the Deep Carbon Observatory, the Energy and Geoscience Institute. This is a Marcellus shale site where they are testing various technologies to quantify the environmental impact of shale gas exploration. We are interactive with the International Energy Agency. I will be in Argentina throughout the week to deliver this same presentation there. And we are very lucky and fortunate to have a collaboration with Texas A&M in Qatar. This is the spread out of the partners of the Science for Clean Energy consortium. Perhaps I should point out those black dots. Those are field sites where we intend to test some of the technologies that we will develop during the next 3 years. So we have a site in Switzerland, a site in Serbia, a site in the UK, and a site in Iceland. We have quite a vast array of education and outreach efforts. I like to point out this Global Management of Natural Resources. It is a master's program where the students exchange between UCL and Australia, and perhaps we could investigate whether we can send some of these students to Qatar in the near future. And we have a Dissemination Forum. That's a meeting that happens once a year in London, and we will continue that for the next few years. So perhaps I should stop here. These are the 3 main pillars that we've been developing: understanding the asset, innovate the technology, and minimize the risk. I think that the next steps are for us to identify ways in which we can promote collaborations and to use this framework that we put together, and I think it's working quite successfully so far, but we need to move it forward so that we can apply the fundamental research that we've done so far to benefit various applications. With this, I thank you for your attention, and I wish you a happy and productive day.
Alberto, thank you very, very much for the nice overview presentation, which is open for questions. Yes, I'm sure.
Thank you for the presentation.
Can you?
I thought I'm loud enough.
And maybe you can mention your name, because there are people that are here for the first time.
Okay, my name is Mansour Karkoum. I'm a faculty at Texas A&M Qatar. My question is regarding the first experiment that you showed with respect to the cracking. That's an experimental setup that was built someplace. Now, the cracking happens in 2 parts. One is the drilling and one is the fracking. So which part are you trying to simulate there? And what are you using? Are you using water jets, or are you using basically mechanical indenting, just like a regular experiment in the lab?
Okay, so that experiment is done in Manchester, and Kevin, I think right after me, is going to give us more details about that.
I can answer a bit. I mean, it's just indentation, and then imaged. Yeah, so it's not using. It's a small scale nano indentation technique. I can show it more, but not much more. But you can discuss after if you want.
So you're not simulating the environment of the fracking or the...
No, that one's not done. That's not done at any pressure at all. Okay. That's not an experiment which I've done. It's a simulation experiment.
Yeah, so that specific experiment is an indentation, but I saw some results from your group that were actually applying pressure from a fluid, and they were looking at how the pore networks changes when different pressures are applied. Those results probably are not ready for public dissemination, but they are quite impressive.
Dominique Guerriot, I am a professor at Texas A&M in Qatar. Thank you for a very interesting overview. I have a question. In the introduction, you say that Poland has stopped to look at this source of energy like shales. But in practice, we know that Poland is burning a lot of coal. So in terms of the economy ranking, there's a carbon tax that may change the game. Do you have, as you are close to the European Commission, do you have any information about these new steps that will change the game?
I should not speak on behalf of the European Commission, so that part I do not know the answer. The Poland example, I think most of the industry pulled out because the production was not economic. Part of that is because the decrease of the oil price during those years, and part of that was because the productivity of the formations was not very large. If the prices change, if the technology is improved, perhaps those formations will become interesting again. Who knows? The future will tell us. Certainly from the point of view of emitting CO2, it will be good to reduce the amount of coal that we burn, especially to produce electricity. And Poland unfortunately, they don't have a lot of access to natural gas, and recent geopolitical events tell us that it is important for different countries to be able to have different sources of natural gas. But that's an area that is certainly out of my expertise.
Yeah, I have a question regarding the permeability. You mentioned that you're going to use the stochastic method to calculate the effective permeability. However, what you're going to feed this stochastic analysis is your local calculations using molecular dynamics, if I understand well. Now, it's easy if you have single porosity. What if you have complex structures with double porosity, for example? How would you do that?
Excellent question. Maria will tell you the answer. What we've seen so far, we've been comparing analytical models that are being used, like the effective medium theory and other approaches, and the stochastic approach seems to be much better as far as model porosities that we input in the material. We have been able to say, okay, some pores are clay-based pores, some pores are kerogen-based pores. We fit a pore size distribution in each of them. We assign a permeability in each of the various pores. And the stochastic method seems to be able to give us something that is quite within experimental measurements. It seems to be working quite nicely. Now, it is still in 2 dimensions, it needs to be made in 3 dimensions to be really accurate, but I think it has some potential to be developed further. It will also have some limits. When the pores are too large, maybe the stochastic approach is no longer being useful. But Maria is going to give us all the details.
Last one.
Thank you. My name is Bassem Shomer from Kiri, HBKU. I'd like to start from the last slide, which is minimize the impact. I'm not sure if you mean the upstream or the downstream. And how do you measure or how do you control the impacts? So in general, the other 2 small questions, I may wait for the next speakers, but you mentioned the innovation technology or innovative technology in the anti-scalants. The other one is related to the water treatment associated with the gas processing. So I'm not sure if you can give also some hints on both the anti-scaling or new anti-scaling materials and the process of water treatment. Thank you.
All right, that's a lot. For the anti-scalant, the Florentine group is going to tell us something later. The names are there, I couldn't read them. The polyaspartate is the one that is being used here. This one here doesn't have any anti-scalant there, so you see that and those scales are calcium sulfate. So we are just at the preliminary work here, so it's qualitative, but you can easily see that the scales over there where nothing is used to prevent the formations, they're much larger compared to when they use the polyaspartate. And this one here is polyacrylate. And so at least looking at this single picture, it looks like the polyaspartate is working at least as well as the polyacrylate. Over there, that's a formulation that contains the polyaspartate together with the hyaluronate. And it looks like the morphology of the scales changes quite significantly. And the hypothesis now is that the hyaluronate creates a network in the aqueous fluid, and the scales grow inside of that network, and the polyaspartate prevents a little bit of the formation of those scales. So it seems like the two are working together synergistically rather than antagonistically in this specific case. Regarding the water purification technologies, essentially what we are doing is to use optimization schemes to consider many different approaches. We are considering possible different uses of the reclamated water. We are not considering reinjection because of the evidence that it can induce a large number of microseismic events if done improperly. So we are assuming that in the European Commission, reinjection will be not very favorable opportunity for the future. So we are considering cleaning up the water for agriculture, cleaning up all the way to drinking level water. We are considering different amounts of wells. So the solution will be different if you only have one well versus if you have a large number of wells in the neighborhood. And we are considering different amounts. So each one of these scenarios is going to give you a different optimal solution in terms of reducing the energy that is needed to clean up that specific water. Importantly, we are trying to connect with the development of this anti-scaling agent, because one issue is that it is possible that norm comes together with the flowback water. As we clean up that water, if we want to go all the way to zero discharge of the salts, so we want to precipitate all the salts, if there is a lot of norm present, it could lead to an accumulation of the radioactive materials. So what we are trying to do in collaboration with the Florentine group is to find out ways in which we can precipitate norm in the formation, but without forming scales too large that prevent the production of natural gas. I don't know, it's a long way to go, but at least we are putting all the pieces together. Regarding the minimization of the environmental impact, we are trying to figure out what are the possible environmental impacts. The technology that is allowing us to detect leaks is going to be essential to figure out what are the leaks, the emissions that are connected with these technologies. In the life cycle assessment, the results of those assessments, they depend strongly on our assumptions for the leaks, for the water used, and so on and so forth. So the better numbers we have to connect to the various risks, the better are our estimates, and as a consequence, it will be easier for us to figure out what is the best way to proceed with the technology. Mentioning life cycle assessment, I put this figure up, but I didn't say anything about it. This is just a little bit of an exercise that we did. We are looking at the Boland formation, and we say, okay, let's assume that we are producing gas from that Boland formation, and let's now look at producing that gas and bringing it to the consumer. So that in this figure here, I'm showing the kilograms of fresh water that are used to produce 1 megajoules of natural gas to the consumer. And you see that there are different bars. And the x-axis here is an estimate of the permeability of that formation. So when the permeability is low, you need a lot of water. When the permeability is high, you need less water. So the conclusion, macroscopically, is that the more gas we produce with better technologies, the less is going to be the environmental impact of that specific development. So to some extent, if we learn how to produce shale gas well, the environmental impact that is connected with it is also going to decrease.
Good. Alberto, thank you very much again.
Thank you.